Hello, good morning, and happy last day before your spring break. I'm excited for you guys to go on break, have some fun, and also get some rest and relaxation in before I see you again on Tuesday, March 21st. A couple of reminders before we begin our notes today. After the video, you will begin work on the homework assignment from the textbook that goes along with this section. And that's on your gold sheet if you need to look at it. Feel free to share books with each other in case somebody does not have their book today. You can also look at the online textbook. At the end of the class period, your substitute will hand out a quiz review and a take-home quiz. Note that the take-home quiz will be due Tuesday when you return. That's March 21st. And I'll say more about that at the end of the video as well. We're going to go ahead and begin our notes for Chapter 6, Section 4, Dot Products and Work. And I'll begin by saying that a dot product is an opportunity for us to multiply two vectors together. So if you think back to vector operations that we did earlier in Section 6.3, we did scalar multiplication, we did vector addition and vector subtraction, and dot product is basically vector multiplication. Go ahead and take a moment to write down the definition of a dot product. Notice you can see why we're calling it a dot product. We've got u dot v, which is basically u times v. And then we have those two vectors in component form. In order to calculate the dot product of u and v, you're basically going to take horizontal components. So u sub 1 times u sub v, and add that with the product of your vertical components, u sub 2 and v sub 2. When you do the dot product, an important thing to note is your answer is a scalar, which is a real number, as opposed to another vector. So when you multiply two vectors together, your answer is a scalar, not a vector. We'll look at an example of how to calculate the dot product. Find the dot product of u and v, given u is 3, 4, and vector v is 2, negative 3. I'm going to go ahead and set up my notation for a dot product. U times v is equal to, and then I'm going to grab my horizontal components from u and v, multiply those together, so 3 times 2, plus grab my vertical components from both vectors, multiply those together, 4 times negative 3, and then evaluate. The dot product is 6 plus negative 12, which is negative 6. Again, pay attention to your solution. Negative 6 is the dot product. That is a number. That is not a vector. I'll give another one for you to try. See if you can find the dot product given the linear combinations of u and v. So u is negative 6i minus 3j, and v is negative 8i plus 4j. To calculate the dot product here, again, I want to grab my horizontal components, which remember in standard unit vectors is always paired with our I. So we would do -6 times -8 plus, grab that vertical component, -3 times 4. And you get positive 48 plus -12, so a dot product of 36. So not a hard calculation, like much of the work we've done with vectors. Just make sure you pair horizontal components and vertical components together when you multiply. Moving along, I'm going to talk really quickly about some of the operations for a dot product. This is not something that you need to write down, but you can put in your notes that this is from page 431. So again, we're going to talk real quickly about some of the properties for the dot product. We're going to let u, v, and w be vectors in the plane or space, and if we see a c, it will be a scalar. So our first property should be pretty intuitive. It basically says if you take u times v or v times u, it's the same thing. And you could kind of look back at those previous examples and see that changing the order in which you multiply horizontal and vertical components will not change the dot product. The second property is that if you take a vector times 0, the solution will be 0, or the 0 vector. So 0, 0. 0 for horizontal and 0 for vertical. Our next property says u times the quantity v plus w is equal to u times v plus u times w. So basically like a distributive property. You could either add v and w first, then multiply by u, or you could distribute to get your dot product and then add together. Number 4 is an interesting one. Vector v times itself is equal to the magnitude of v squared. I'll do a quick example of what that looks like. So I've got v is equal to the vector a, b. Okay, so we'll just use those as placeholders. If I were to do the dot product, v times v, then I would essentially be doing horizontal component a times a plus vertical component b times b, which when I simplify that, I would get the dot product v times v is a squared plus b squared. And a squared plus b squared should look pretty familiar to you. This is what's underneath the radical for magnitude. So the dot product of v times v is actually the magnitude squared. And so that the radical isn't there any longer. Number 5 is a scalar c times the dot product of u times v. You could basically just, you're going to multiply two things at a time, and then you'll have to multiply twice. So you could do the dot product for u and v, which is a scalar, and then multiply that by c. Or you could multiply your scalar by c, or by vector u, and then do the dot product. Or multiply your scalar to vector v, and then do the dot product with u. And that's the end for our properties of a dot product. So not necessarily something you have to memorize, nor something that you should write down, but good thing for us to chat about. Now, here are some ways that we can use dot products. So this is an application for a dot product. We're going to use the dot product to find the angle between two vectors. I'll give you a minute to write that down. So this definition says we're going to call theta the angle between two vectors, both of which are non-zero vectors. Then we can find theta because we know cosine of theta is equal to the dot product, that's in our numerator, of the two vectors u and v divided by the product of their magnitudes. That's in the denominator. So the magnitude of u times the magnitude of v. In order to actually solve for theta, after you do the dot product divided by the product of the magnitudes, you'll have to do the inverse cosine in order to solve for theta. And a couple of things to note about this formula. The formula finds the smallest angle between two vectors. There are actually infinitely many angles between the two vectors. And I'll just go ahead and draw a visual so you can kind of picture what this means. Suppose I have a coordinate plane and I have two vectors, u and v, and I want to find the angle between the two vectors. This formula, when I solve for theta, is going to get me the smallest angle between those two vectors, as opposed to this larger angle or one of the coterminal angles if I were to do a full rotation and then go to another vector. So we're always going to get the smallest angle between two vectors, and our angle generally will be between 0 degrees and 180 degrees. Most of the time it will be between those two numbers as opposed to equal to those two numbers, 0 and 180. If the angle is 0 or 180 degrees, then the vectors are parallel. If the answer is 0, then the vectors are going in the same direction, parallel and same direction. If the answer for theta would be 180 degrees, then they're parallel, but they're going in opposite directions. Okay, so just something to think about there if you get a 0 or a 180. Okay, let's put this to use in an example. So we want to find the angle between the vectors u and v, and I believe this is our u and v from a previous slide, the example that you did on your own. So I think we've already found the dot product for u and v, which was 48 minus 12, or 36. So I'll go ahead and jot that down. Dot product, u times v, was equal to 36. In order to complete and find the angle, remember, pay attention to the direction. So we want to find the angle between the vectors. That tells me to use that formula we just copied down. The cosine of theta is equal to the dot product divided by the product of the magnitudes. So we have the dot product already as 36. Now we'd really like to know our magnitudes. So I'm going to do the magnitude of u, which is the square root of -6 squared plus -3 squared. And that would be 36 plus 9, so the square root of 45. And the magnitude of v is equal to the square root of -8 squared plus 4 squared, which would be 64 plus 16, so the square root of 80. Now, normally I would say when you're finding magnitudes, go ahead and simplify those radicals to look for perfect squares, and both of these radicals will simplify. The square root of 45 is 3 square root 5, and the square root of 80 is 4 square root 5. because we're really just putting these into a formula that we're going to evaluate and do the inverse cosine for, it's not really necessary that you simplify your radicals here. So I'm probably just going to leave my radicals as square root 45 and square root 80. Feel free to reduce those or simplify those in simplest radical form, but not necessary. So I'm going to go ahead and plug in all the information that I have. The cosine of theta is equal to the dot product, which we know from our previous example is 36, divided by the square root of 45 times the square root of 80. Okay. You can do this piece by piece if you want. I generally would say at this point you have enough stuff going on. It may just be easiest to plug it into your calculator. So I'm going to take the inverse cosine or the arc cosine of both sides right now in my calculator. The only thing you'll have to be really careful of is when you do the arc cosine of 36 divided by that product, you're going to need a set of parentheses around your denominator. So the square root of 45 times the square root of 80 needs to be in its own set of parentheses. Go ahead and type that into your calculator right now if you want to see if you could evaluate. If you don't want to do the arc cosine right away, you could also just do 36 divided by that quantity and then do the arc cosine of your answer in your calculator. Also note that like when I'm working out my in my calculator, I don't have the math print that I can put stuff underneath my radicals. So then when my radical opens this parenthesis for 45, I've got to close it before I multiply by the square root of 80. So you might have to watch your parentheses there as well. But when I type that all into my calculator, I come up with a theta of 53.13 degrees. Now, if you're ever curious if that's the right answer or if your answer is reasonable, go ahead and go back to your two vectors, u and v. These are written in linear combination form, and sort of sketch or graph them and see if that seems reasonable as to where your angle is. So if I were to sketch u at -6, -3, I'd go 6 left and 3 down to my terminal point. So there's my vector u. At v, I'm going 8 to the left and 4 up. So 8 to the left and 4 up to my terminal point. So there's my v. And does it seem reasonable that this angle in between, the smallest angle in between my two angles is 53.13? Yeah, it looks pretty good. So again, just be really careful if you're typing that onto your calculator all at one time. Something to practice and help each other out if anybody's having trouble with that. Let's go ahead and move on and talk about orthogonal vectors. Orthogonal is a special word that we use when talking about vectors that are perpendicular. And think back to geometry. Perpendicular would mean those vectors are intersecting to form a 90-degree angle. Two vectors are orthogonal if and only if their dot product is 0. So remember u times v, that's representing their dot product. Think about why this works using that formula from the last slide. We have cosine of theta is equal to the dot product u times v divided by the magnitude of u times the magnitude of v. And then think about, we're talking about two vectors that are orthogonal, they're perpendicular, they're crossing at a 90-degree angle, so we would know that this theta is in fact 90 degrees. And now think back to chapter 4 with your unit circle. What is the cosine of 90 degrees? So think about your x-coordinate. The cosine of 90 degrees, we know, is equal to 0 on the unit circle. And so this value of 0 must be what we were figuring or thinking, like the cosine of 90 is equal to what? The cosine of theta, it must have been equal to 0, so that we got 90 as the answer. So for a fraction to equal 0, the only way that's ever going to happen is if your numerator is equal to 0. So here's a question. Are the vectors u and v here orthogonal? To check these two vectors for orthogonal, you want to show some mathematical work. So just a simple yes or no is not an acceptable answer. Also, I don't want you to graph it and check. I want you to do the dot product work. So we're doing the dot product. I want to know, is the dot product 6 times negative 1/3 plus 10 times 1/5 equal to 0? That's negative 2 plus 2. So my dot product is 0. The answer would be yes. These are orthogonal. Oops, spell wrong. If you got any other number besides 0, your answer would simply be no. They are not orthogonal. All right, one last concept to talk before we wrap things up, and that's the concept of work. Work is equal to force times distance. Some of you may have done formulas for work in physics. If you have seen the formula for work in physics, the distance may also be called displacement. So our textbook, mathematical textbook, uses the phrase distance, so I use the phrase distance. If you prefer to think about it as displacement, that would basically be the same thing, so not a huge issue. And then you could also think about this formula as work equals F times D, which may be how it's represented in physics class. So then that D could be read as displacement or distance. Now before we get into the example with work, just note that when we're talking about force, we're talking about the force that does the displacement or moves the object a certain distance, and you only use the component that goes along with the direction that the object is being moved. So if I am going to push a table across the room, I would only want for force the horizontal component of my vector, because I'm moving the table horizontally across the room. If I were lifting books from the floor, then I would use only the vertical component of my force, because my displacement is vertical. So let's look at an example, and I know there's a lot of words on the screen right now, so this is actually an example from the textbook. It's page 439, number 84. If you want to write that down into your notebook and just kind of go back and look at page 439, number 84, you could do that. We basically got a scenario here where we've got a ski patroller that pulls a rescue toboggan across a flat snow surface by exerting a force of 35 pounds on a handle that makes an angle of 22 degrees with the horizontal. Find the work done in pulling the toboggan 200 feet. So first thing you want to do in a lot of these problems that involve work is sort of sketch yourself a little picture. If you look in the textbook offers a much nicer picture than I could draw for you. So I'm going to go ahead and use that picture from the textbook. So here's our ski patroller dressed in red right here. And you can see he's pulling a rescue toboggan, and we know that the ski patroller is exerting a force of 35 pounds on the handle that makes an angle of 22 degrees with the horizontal, so you can see that angle labeled there. And we want to find the work done in pulling the toboggan 200 feet. So we're thinking about work is equal to force times distance. And so we know in this image that our force is 35 pounds. Okay. We know that our distance is 200 feet. And when we calculate the work, we don't want to just use the force 35 pounds. We only want to use the horizontal component of force because we're pulling that toboggan horizontally. So then we're going back to our work from 6.3, and we are calculating the horizontal component of force, which is 35 times the cosine of 22. So the horizontal component of force is 35 times the cosine of 22 degrees. So when we plug into that formula for work, we actually want to use that horizontal component and the distance or displacement of 200 feet. So I would say my work done is equal to 35 times cosine of 22 times 200. Okay. And so go ahead and do that in your calculators. And I get something like 6,490.29. And my label here, because I was multiplying force times distance, we're going to check our labels. What's our force in pounds and our distance is in feet. So then our label here would be 6,490.29 foot-pounds. And I know that that's a little bit strange, and if you've taken physics, then you are used to their standard label of, I believe it's Newton meters, but of course we need to read our problem. There are other ways to measure work, and so we just follow whatever is there. So that's basically it for today. Just a really quick reminder that you are now to get out your textbook. You're to begin work on the assignment for section 4 from your gold sheet. Go ahead and share textbooks or look up the online textbook on your phone as needed. And at the end of the class period, your substitute will hand out the review. The review for the take-home quiz is optional. I will have homework answer keys and review answer keys available online over spring break if you need to use them to make sure you're doing things correctly. Your substitute will also hand out to you the take-home quiz, which is required and will be due at the beginning of class on Tuesday, March 21st, and will be graded as is when you turn it in for a grade in the grade book. Okay. Hope you guys have a wonderful spring break. Please enjoy the time off. Get that rest and relaxation that you need, and I will see you again on March 21st. Have a great break.